In Chapter 8, we were doing confidence intervals, which helped us estimate a true mean or a true proportion. In Chapter 9, we're going to do something a little bit different. Instead of estimating a mean or a proportion, we're going to be testing a claim. The video you're about to watch was mostly recorded last year. I recorded this in 2020, but it was before 2020 became 2020. But it's a good video, other than, as you can see, I didn't know how to crop things yet. I don't know. I'll try to fix that. But anyway, if the style of this video doesn't really fit what I've been doing in the other videos, that's why. It's past me in the before times. The content is good. Formatting may be a little bit different than usual. Anyway, time for significance tests. So the whole point of doing statistics is to do inference, which is where you're trying to make conclusions about a population. So far we've done confidence intervals, which is how you estimate a parameter. For example, what's the mean number of minutes it takes for Domino's to deliver a pizza? We want to estimate a parameter. The other main thing that we can do with inference is a significance test, and this is for assessing evidence or assessing a claim. For example, maybe Domino's claims that they can average 20 minutes to deliver a pizza, and we want to see, is it actually higher than that? So let's start with a claim. You guys don't know this, but I can make 80% of bottle flips. So when I flip a water bottle, 80% of the time it lands. So you don't have to tell me if you think that's true. I'm just going to show you a small sample of my bottle flipping capabilities. Okay, so we return to the question of, do you think that's a true statement? And if you were keeping track, I made 0.095. That's my proportion of bottle flips that I actually landed. So hopefully you now suspect that I'm lying. I am lying. I can't make 80% of bottle flips. And this is the main idea of significance tests. An outcome that would rarely happen if the claim were true probably means the claim isn't true. If I really could make 80% of bottle flips, it would be really unlikely that in 21 flips I would only make 2 of them. It's so unlikely that my original claim was probably a lie. You'll notice that this is in a different color and also has a star next to it, because it's really important. It's the main idea of significance tests. So you might want to pause the video and write that down. So the actual definition of a significance test, it's a formal procedure for comparing observed data with a claim or a hypothesis. And what you do when you make a significance test is you set up a null and an alternate hypothesis. Once again, if you need to pause this because you're writing down some definitions, that's totally fine. A null hypothesis is a statement that's being tested, or a status quo. That's kind of like what you already think is true or what people think is true. And then your alternate hypothesis, or your alternative hypothesis, is the claim that you're finding evidence for. Both of these are always stated in terms of your population parameter, never in terms of your sample. We're going to look at some examples. So the bottle flip example. The parameter was the true proportion P, the true proportion of flips that I can make. And notice that I'm using P. It's a population parameter. I'm not talking about P hat. I know what P hat is. It was pathetic. It was 0.095. We don't need to talk about it anymore. My null hypothesis was the original claim. I claimed that my true proportion of bottle flips I could make was 0.8. And then, depending on your faith in me, your alternate hypothesis is going to be different. Probably you suspected I was much worse than that, and so you suspected that the true proportion of bottle flips I can make was less than 0.8. So you'll notice that both of these are about P, proportion from the population. Those should both match. They should always be about the same parameter. These numbers should always match. And really all that's changing is the null is that the claim said that the proportion was equal to 0.8, and then your suspicion is that it's less than or greater than. And if you say it's less than or greater than, that is called a one-sided alternative. All right, so let's look at another example. The mean GPA in State College last year was 2.85. I know that as a fact. Somehow I looked up the data and I know that, but I think it's higher this year, and we're going to test to see if that's true. So pause the video and try figuring out the parameter, the null, and the alternate on your own. So this time we're dealing with a mean, not a proportion. It's the mean GPA. So we're going to use mu. And usually what I do is I write mu twice just to remind myself that it should be mu both times, not x bar, not p hat, not anything else. The null is that things are exactly the same as last year. Mu is 2.85. However, the alternate, I suspect that the GPA is higher this year, so my alternate is going to be that the mean is actually greater than 2.85. And once again, this is a one-sided alternative because I just think that the mean is greater. Let's look at one more example. Pause the video, try this one on your own again. Okay, so the mean is the true mean salary for professional hockey players. Last year it was 2.4 million. Just going to abbreviate. We're just wondering if it's changed. We don't have a suspicion that it's higher or lower, we just want to know if it's different. So our alternate is going to be mu not equal to 2.4 million. And this is called a two-sided alternative. Because if you think about the sampling distribution of x bar, we don't know if the true mean is actually higher or lower. It could be either, and we're just curious if it is either higher or lower. So it's a two-sided alternate. All right, now in general, when you're doing a significance test, your null hypothesis is innocent until proven guilty. So it's innocent, it's whatever we believed last year or whatever society currently believes, and we're trying to provide convincing evidence against it. So you start out assuming that it's true, and you're trying to find evidence that it's not true. Now, to decide if we have enough convincing evidence, we have what's called a p-value. We're not going to get into the calculations of how do you find the p-value today. That'll be in a different section. For now, we're just focusing on the idea of a p-value. The p-value is the probability that a statistic would take a value as extreme or more extreme than the one observed. So let's think about the bottle flipping example. Let's just say it was a normal distribution. Most of the time I can make 0.8 of bottle flips. Sometimes it's higher, sometimes it's lower, but mostly it's around 0.8. The p-value would tell me the probability that I get a p-hat of 0.095 or something more extreme. Hopefully you can see that the 0.095 is really far away from 0.8. That p-value would be tiny. It'd be a really small chance of me making that few bottle flips if the 0.8 was true. So you can kind of see how we're going to be calculating a p-value. It's an area under a curve. This curve happens to be normal. We've done that a lot, but for now we're not going to worry about how the p-value is calculated. What I want you to focus on now is just the idea that a small p-value means there's a small chance of getting that x bar or that p-hat, which means that's good evidence that the null is wrong. It's good evidence against the null. So a small p-value means you have good evidence that the null is probably wrong. So let's go back to the GPA example. Let's say I do take a sample of students and find their GPA. So I get, let's say, an x bar of 2.91. I do some calculations. I get a p-value of 0.05. Now that is a small probability of getting an x bar of 2.91 or something more extreme. So picture that normal distribution again. Here's 2.85. 2.91. The p-value is the probability of getting 2.91 or something more extreme. It's pretty small, only 5%. We have two different options for making a conclusion, and these are in quotes. This is like how you should say your conclusions. We either reject the null or we fail to reject the null. You should not say that you accept the null. So you're either deciding we have evidence against the null, we're going to reject it, or basically you're saying we haven't found enough evidence to reject the null, so we're going to fail to reject it. We're not accepting it as 100% true, we're just failing to reject it. Now the question is, how small should our p-value be? It's like in this example, 0.05, that's small, but is it small enough? And you guys have asked this question when you've come across homework problems that say, is this unlikely to happen by chance? So before you start a significance test, you get to pick what's called a significance level. And we use the Greek letter alpha, which looks like a little fish, to represent the significance level. The most common ones are 0.05 and 0.01. All right, so if the p-value is smaller than the significance level, then we say that the statistic is significant. And we've talked about this before. That doesn't mean the same kind of significant that you use in everyday life. A statistic is significant if it's unlikely to happen by chance. So you have to pick the significance level before you start. It's kind of cheating to do the entire test and then at the end see what your p-value was and then say, oh, I'll choose a significance level that's conveniently above it. So you have to set that ahead of time. So if we were going with 0.05 as our significance level, in this GPA example, this would not quite be convincing evidence. It's exactly equal to. You could maybe argue that it's right on the significance level, so maybe that's good enough evidence. But if you had selected 0.1 as your significance level, then you could say this is convincing evidence against the null, and we will reject the null. If you had chosen 0.01 as your significance level, now the 0.05 is greater than the significance level, so you wouldn't have enough evidence. You would say we fail to reject the null because our p-value is not significant. So just to recap, you set your significance level first, let's say 0.05, and then you find your p-value, which we'll get into in later sections. If you find a p-value that's smaller, this is good evidence against the null, so we would reject the null. And if you find a p-value that's greater than the significance level, that's not significant evidence against the null, so we fail to reject the null. Remember, don't say accept, you're saying fail to reject.